This is the Earth Science Classroom. Welcome back. This video is all about how to review and study for an upcoming test on volcanoes or volcanology. So this video is going to look at the different topics and different parts of the unit I teach in volcanology, and it covers all aspects of magma and lava, plate tectonics, crustal deformation, the origin and creation of magma to form volcanoes on the surface, different types of volcanoes, eruption types, and types of lava. So as you're watching this video, each part will have links to the other videos I've done in more detail on each part of volcanoes, and you can look at that and use those videos in addition to this one to get ready for any kind of future volcano test. First, we're going to look at some background knowledge, link up rocks and minerals and what they are to volcanoes. We can look at rocks being composed of minerals. So looking at the elements, composition, different types of rocks from igneous to sedimentary to metamorphic. We can even discuss the rock cycle and the movement of different materials through different areas of the earth and time scales and different processes like weather and erosion, looking at heating and pressure, looking at the temperature, and looking at the starting point, which is in this case going to be magma. Now, if we look at the Earth's interior layers, we need to concentrate on the upper mantle, which is right here. I've got UM, upper mantle. Now it includes, obviously, we have the crust, we have the lithosphere, we have the asthenosphere, and we have the mesosphere, but the mesosphere is part of or makes up the lower mantle. The lower mantle is composed of the mesosphere and different composition of ultramafic igneous rocks. And you have the upper mantle really starting here, and then down here will be the lower mantle. The crust is technically a part of the lithosphere, and you have the two different types of crust, the thinner versus the thicker. Generally, you have oceanic being the thinner, more basaltic, and we have the continental crust being mostly granitic or andesitic. Put andesitic in here as well. And I put this kind of dashed line here to separate the crust. The lithosphere is somewhat consistent in its composition and density, whereas the oceanic and continental upper crust area does differ in composition and density. Oceanic being around 3.0 grams per centimeter cubed, and continental being around 2.7 grams per centimeter cubed. Now, why do we care about the Earth's interior? Well, because you've got crustal deformation. Crustal deformation that leads to plates and plate tectonics, which leads to various areas and processes that create magma. Now, magma is only a very small percentage overall makeup of the Earth. It's around 1%. However, that 1% does create our subject of volcanology, which we are looking at today. So the 1% magma created in the Earth is very important for us. So in regards to plate tectonics, we have the convergent plate boundary, which is termed an active margin. And you have the two types of convergence, which is ocean to ocean and ocean to continental. And these two are the main processes that create, or main boundaries that create subduction. Now, subduction is a difference in density, which refers to isostasy and buoyancy, and which plate would technically be pushed and pulled under the lighter one, the lighter or less dense. So in this case, the ocean convergent plate is going to be denser than, let's say, the other ocean, and especially the continental, based on age and thickness and density, and subduction will be created, and subduction at different angles will create the environment to melt the slab. The slab, which is the plate that's subducting, that's oceanic, that's mostly basaltic, extrusive igneous rock, and it's going to melt. Now, this is done through various processes, but mainly through what's called flux melting, which is the addition of volatiles. So you add basically water and other dissolved gases and hydrous minerals, and you're going to lower the melting point of the rock, mostly in the continental or oceanic, the rock that's floating above. The friction plus the gravity plus density plus the shear scale adds all the heat, and it's going to raise the heat up to around or above 800 degrees centigrade, up to 1500 degrees centigrade, which is going to provide the environment where rocks will start to or partially melt, or at the maximum temperature will fully melt, and these rocks will become magma. This can also happen in a hotspot situation. So it's an intraplate volcanism where you have a plume of magma rising up, a diapir or a hotspot like in Hawaii or Yellowstone, and that would be decompression melting, and that would create the magma that is used in these volcanoes. So what is magma? We create magma through melting of rock. So you have a rock and you're going to add the heat or thermal energy in different situations, and you're going to create the liquid or molten state called magma. Now this contains, so you have the yellow being the liquid part of the magma, the main part of it, component of it, and this is called melt. And this is formed from basic molten or liquid minerals. And the minerals the different or variation in minerals will come from the parent rock, which was melted back over here. The blue little circles I've drawn in will be the dissolved gases, and these will be mostly water vapor. It will be some CO2, some SO2, and some NO2. Now these four are what we call greenhouse gases, and are responsible for the Earth maintaining some sort of homeostasis and level of temperature which is convenient for our current species and life to flourish or evolve under or evolve within. The black little dots there I've added are crystals. Now crystals are the solid minerals that are still either partially or solid within the different magma temperatures. If it was up towards 1500 degrees, it'll be less and less crystals, whereas if it's at 800 degrees, there'll be a lot more crystals present in the magma. And that is called differentiation, and it's called crystallization. And you can check out the Bowen's reaction series to see which minerals occur at which temperatures. So the characteristics of magma. Now I mentioned that the magma is minerals, and minerals are made of compounds and single elements. Now, a particular molecule we should look at is SiO2. Now, the Si, that is silicon, and the O. So why are these two important? Where they come from? They come from the elements that are in the minerals that are melted in the rock to create magma. So they're there basically from the start. And when you melt them, you still have them in a melted form. Now, together they make SiO2, which is the chemical formula for silica, and it's made of the two elements silicon and oxygen. Now, silicon is Si and oxygen is O. Now, silicon is 27.7% and oxygen is around 46.6%. So it is going to be, when you add these bad boys up, looking at around 74% of the crust being made of these two elements and being part of the 90% silicate mineral group. If the crust and upper mantle is mostly made of silicate minerals, which is mostly composed of silicon and oxygen, and the two main elements, that when you melt rock in these areas, you're going to have an abundance of silicon and oxygen being present as a molecule, which is going to be called silica, SiO2. Now, why is this important as a characteristic? Well, silica is one of the main factors which controls the viscosity of the magma, which is the resistance to flow. So it's how much a liquid wants to flow under the force of gravity. And let's say water has a viscosity of 1, let's just say, for example, then any kind of magma or lava would have a viscosity of 10,000 up to 1 million times more viscous. So magma and lava, in theory, can be up to 1 million times thicker than water is, and yet magma and lava are still considered a liquid. So in terms of characteristics of the magma or lava, a range of viscosities from low, medium, and high. High viscosity means it's very thick and slow moving. Low means it's runny and faster moving. So in terms of relationships is how they work together, how they impact each other, and the effect that they have on each other. For example, the higher, I'm going to put an arrow up, that means higher, and this means lower. So the higher the silica, or SiO2, equals, so relationship, higher viscosity equals, the thicker it is, the more gas content it will hold. So from 1 up to 4% gas as a content. And the more gas equals a larger, more explosive eruption. And this would also equal a lower temperature. So the magma or lava would be colder as it is thicker with more silica. So all these are connected. And this kind of magma is called andesitic or dacitic or rhyolitic. Now, this is increasing in silica percentage by weight up to around 70 to 75%, which is rhyolite, or 60 to 70%, which is andesitic. So this is the higher viscosity, higher silica magma types. So the lower the silica, the lower viscosity, the runnier it is. This is very runny. Equals less gas, so therefore it's less explosive and lower on the VEI scale, and it'll be a higher temperature. So it'll be the 1000 degrees plus up to 1500 degrees centigrade. And then this one would be from 50 to 60% silica, so SiO2. This is all silica percentage, and this would be called basaltic. Another word for basaltic is mafic composition, and the opposite end of that spectrum is rhyolitic, which is called felsic. So here's our 4 types of magma: basaltic, andesitic, dacitic, and rhyolitic. This leads us onto our 4 types of lava. So when magma goes on the surface, it's lava, and we just change the names. Basaltic is going to be, let's put basaltic, it's going to be more like pahoehoe, more a Hawaiian word, very runny, same characteristics as basaltic. Andesitic, and this could be a version of andesitic and dacitic, would be what's called aha, which is very rocky, sharp and jagged crust, somewhat medium temperature, medium viscosity. And then the one that's rhyolitic would be blocky. Now another basaltic lava, a magma that comes out as lava, would be what's called pillow lava. That only really occurs on the ocean floors, in mid-ocean ridges, and various other volcanic areas on the ocean floor where the cold ocean meets the hot magma and lava flowing out, and it creates these very large very large like air sacs of lava that cool extremely fast and move across the ocean floor, making like a pillow shape. So if we're looking at the general anatomy, when that magma is forced up onto the surface, there is a way through and the lava starts flowing, you start to create volcanoes. Now the classic anatomy of a volcano includes the magma chamber, which contains the magma, which can base. Now we can base our level of activity on this volcano based on the magma. So in terms of activity, we can have an active volcano, which means that the volcano is currently erupting. There is gas or lava or ash. Something's happening with the volcano. It's alive and working and spewing out material. And the material is called pyroclastic material, and also called ejecta, or comes out of the volcano. This is active. And then dormant would be a term for an inactivity, that the volcano is currently in between eruptions, either recharging, resupplying the magma, and either sleeping, and this could vary in time from a couple of days to years to centuries to millennia. Depends on the location, depends on the volcano. But dormant is sleeping. And then you have extinct. Now the extinct means there is no more magma. No magma, there's no chance for lava and no chance for eruptions. And we have just a solid chunk of intrusive igneous rock, usually a granite or an andesite, diorite. But you have these intrusive rocks, and they're going to form a solid structure. And we also get plutons or plutonic features created. And the magma chamber is going to be connected to some sort of conduit or system that feeds it from either the asthenosphere or from the plume itself if it's a hotspot. So number 2, looking at the rock that the volcano is sitting on or made from. So looking at the crust and the lithosphere to put it into context. 3, that's going to be a fumarole, which is a vent for gas, and the gas coming out is going to be mostly water vapor. Some CO2, some NO2, and some SO2 right there. Now, 4 is going to be a dike, which is more diagonal, or a sill, which is more horizontal. This is a small pipe or small tube that connects from the central tube or the conduit. So right here is the conduit, CONDUIT, the conduit, which attaches from the magma chamber up to number 6 is the central vent, or also called the crater, or part of the summit or top of the volcano. So the conduit connects both. 5 is going to be the ash cloud, which is just generic. So looking at tephra and pyroclastic material, which is TMP, and looking at ignimbrites as well as different sizes of tephra and material coming out of the volcano. And this is all called, again, ejecta. So the main volcano types, there are 6 main types. You've got the nice strato volcano. You've got also called the composite or composite. Now this actually means layered. This volcano is made from layers of ash and lava. So we can dictate that the ash and lava are very explosive eruptions. So explosive eruption we can dictate is more going to be andesitic, dacitic, or rhyolitic magma and the corresponding lava types. So just from the formation of the magma, formation of the volcano, we can derive and figure out the type of magma and lava that is being sourced through this kind of volcano. And the types of volcano are based on the magma that is creating it. Next one is the shield. Okay, it looks like a massive shield as a profile. You have a very wide and tall volcano and made of layers of lava. And here's the crater right here, and the lava spewing out, and there's some small amounts of ash maybe, but this shield is spewing out lava. It's very basaltic, very runny, and therefore low in silica, low in viscosity. And the classic one is going to be the Ring of Fire. The classic one's going to be Hawaii, whereas strato and composite, you've got these are 60% of all volcanoes are stratos, and the Pacific Ring of Fire is going to be the example. Shield is going to be Hawaii as a intraplate volcanism hotspot. Third one, this one is going to be our cinder, which is ash, or called scoria. Now these come in groups, and they are less than 300 meters in height, and they are made of ash, and they usually form on sides of volcanoes. And Arizona is a good example where there's a very big valley of over 600 of these beautiful volcanoes, all in a nice big area. Now we're on to the 4th and 5th and 6th volcanoes. Now these 3, strato, composite, shield, and cinder, they're the most common classic ones. The 4th one is going to be our lava dome. These are high viscosity, thick magmas that come over the central vent and kind of form, and it's right here, and it usually forms in the crater or on the sides of volcanoes, but it's basically just going to be a plug, a volcanic plug that's going to sit on top of the volcano and form usually after an eruption, or can indicate the activity of a dormant, now active volcano. This one's going to be a fissure, classically in Iceland, and basically it's a crack or a fracture in the earth, and the magma is going to rise up, forming very low viscosity, high fluid, high temperature lava that's going to cause lava fountains and sprays and spatter, very, very messy volcano, and it's going to flow out. And these have very large volumes of lava being injected through, and it's more consistent. Rather than polygenic, it's more like a consistent monogenic eruption. Last one is Caldera, which is famous because the larger volcanoes and more explosive, higher VEI eruptions, like 6 to 8, are linked with more calderas, and they're very, very wide. This caldera is a sunken, collapsed volcano crater into an emptied magma chamber, either after a volcano eruption or just a lack of resupply of magma. There's 3 different types of calderas and how they form. So these are the classic ones, like Yellowstone National Park. So, they will form different kinds of volcanoes and types. Now these volcanoes will erupt based on the magma tephra, obviously the volume, which is in kilometers cubed of ejecta. So Hawaiian Icelandic are very small, are medium, violence, medium, volcanic eruptions, subplinian, that's our VEI, 4 to 5, very large, anything above 5 plus, so 6 down to 8. Plinian. Don't forget, Plinian is from younger, Vesuvius, Blaine is from Pele, Volcano is from Volcano, Italy, also next door is Boli. Boli is Icelandic, obviously, from the figures, Iceland, and Hawaiian, here and Kilauea. Ultra-plinian in terms of that super volcano, which would be like Yellowstone, or Toba, or a crater. So, generic features, we have obviously ash cloud, volcanic column, ash column, right here. It's extended various images of the atmosphere. The ash cloud, and we have the fall-in material, or pyroclastic material, fall-in as tephra. And this is also called ignites, it flows as pyroclastic flow and lays down layers of pumice, tuff, various forms of this ash. So in terms of tephra, you have different sizes. So very small, medium sizes, so looking at around 2.2 centimeters and 6.4 centimeters, so around 6.4 centimeters. Looking at things called lapillis, or volcanic cinders. Then the larger ones, anything larger than 6.4 centimeters, can be classified into two ways: either a block, volcanic or lava block, or a lava bomb. A block is a solid piece of rock, and a bomb is a solid shell that inside of it is still a molten rock. Now, these can be varying sizes from 6.4 centimeters up to the size of houses. Now, the next thing would be obviously some sort of lava flow, viscosity, energy left, cause lava domes, you get some flank eruptions out of the parasitic cone. You can have some snow and ice accumulate on the summit around the crater high elevation, and the ash, the lava, and the gases could heat this water and snow and ice and force it down the volcanic slopes, causing what's called volcanic. And this is very dangerous, fast moving, thick material downside. Next thing you can also have is what's called a fumarole, which is gas vents outside leading from the conduit out into the atmosphere. You can have this ash cloud come down with gravity and flow into the heart, so flow down the sides, which would be called a pyroclastic flow. Now, certain smaller volcanic eruptions are quiet, almost lava flows. You will see tremors and you see this ash cloud, but very small, but basically effusive. They are effusive eruptions of this lava. As you get into the more volcanoes from Boli, you get larger eruptions, more energy, more lava fountains, maybe some ash. Then you get into Palaean. Now, Palaean's famous for the pyroclastic flow, known as a noir ardente glowing cloud, and it's killed 30,000 people out of much in 1902. And pyroclastic flows is very dangerous. Now, St. Helens had one, very dangerous. Vesuvius had a couple. Now, Lahars also can be certain types of volcanic eruptions. systems with their eruptions. As you go further down the scale, you get a longer time period between eruptions. So then you get 4 and 5, and that's plain, ultra-plinian, very large eruptions, very dangerous to be around, and has killed people in the past. These are usually stratovolcanoes. And then 5 and 6 looking at plinian, and being extremely explosive with a lot more features, large ash clouds, tephra, pyroclastic flows, lahars, and lava flows, lots of eruptions and landslides. And this is a very large eruption. This is usually calderas, you've got stratus. Then you get the 7 and 8. This is cataclysmic. This is world events. This is changing our planet as we know it, how we reside on the surface according to Mother Nature's will. And these are ultra-plinian, and they are very incised. Some have changed the course of history, and some might in the future. These are definitely very, very large, explosive eruptions. So this is the roundup. This is the review of volcanology. This is how I go through my students step by step, building from magma, rocks, and minerals, all the way through using plate tectonics and crustal deformation, how to make the magma, how to form volcanoes that occur across the world, examples of fire, and types of Vesuvius coming together, and looking at the functionality characteristics of magma, lava, nature, eruption, the ice scale, and how we quantify these events. This is the Earth Science Classroom. Thank you for watching. I hope you enjoyed the content. Check out more videos on our channel, and don't forget to subscribe. Thank you again.